Okay, so solving trig equations. We're going to go back to, like, recalling the skills of Algebra 1 and Algebra 2, like factoring, solving two-step equations, factoring monomials, but now involving trig. Really, really similar to what we did in Chapter 3 when we had that section where we solved equations involving exponential functions and logarithms. You know how much you love that? Yeah. Hopefully your algebra skills have strengthened a bit more over the last couple of chapters. That is the intention of the course. So to do this section well, besides obviously the need to practice, we need to recall on some identities that are going to help us make sure that our equations are in one single variable, which is going to involve example hopefully I get to by the end of the period. And those are the Pythagorean identities. So our Pythagorean identities, what's the first one? What's the big dog that we are going to use? Not that you just are getting into this, but I keep saying it. What are we going to use all the time?
Sine squared theta plus cosine squared theta equals 1.
Yep. Sine squared theta, sine of, I've been saying this backwards, by the way, because it doesn't roll off the tongue very well once you get to powers of like 3, 4, 5, and 10. But it's the sine of theta squared plus the cosine of theta squared is equal to 1. If I haven't made it clear enough yet, when we have like a sine of theta squared, which is really how I should say it, because it's all of sine of theta being squared, the equivalent notation, it's a little bit more time consuming to write, which is probably why mathematicians don't like it. But sine of theta squared is the sine of theta. It's theta that's inside the math operation of sine, and that whole thing is being squared. This is really what sine of theta squared is, and if I say sine squared theta or something like that, I'm really kind of not saying it correctly. This notation really more obviously lets you see what is going on. You're putting in an angle, you're putting in the sine, two sides of a reference triangle are coming out, and then that value is being squared. This notation also is helpful in calculus when you're learning how to take a derivative using the chain rule. This notation makes, when you first learn chain rule, this standard way of writing exponents in trig is a little bit tricky or misleading. This is standard, so this is what I'll be writing, but this is what it means. So sine of theta squared plus cosine theta squared equals 1. Now, there's another Pythagorean identity that involves tangent. If you don't remember what it is, and I think the hands that are up do, but if you don't remember the identity that involves tangent, you just have to ask yourself, that in terms of sine and cosine, tangent of theta is, tangent of theta in terms of sine and cosine, tangent of theta is what? Sine theta over cosine theta. So if you want that Pythagorean identity that involves tangent, you're going to remember that you need a sine squared theta over cosine squared theta. Just do it mentally in your head. And then your hand was up. Sine squared theta divided by cosine squared theta is tangent. So we have tangent squared theta plus dividing by cosine squared, we get 1. And dividing by cosine squared, we get secant squared theta. You're not even hesitating. You know what that is. Now, there's another trig identity, Pythagorean identity, that has cotangent. Well, if sine theta is, tangent theta is sine theta over cosine theta, then cotangent theta is cosine theta over sine theta. So we need to take this, this first identity and divide everything by sine of theta squared. So the first term is going to be
cotangent?
Yep. Well, we're going to get to cotangent.
Oh,
1. And then cosine theta squared divided by sine theta squared is cotangent.
Equals cosecant.
Of theta squared is equal to cosecant theta squared. Nice. Now I'm going to give you our first example is going to need us to use a calculator. So one or all of you grab a graphing calculator, and hopefully all of you, of course. I need it to be in radian mode because we need to get used to radians. And our first example is the cosine of x is equal to negative 2/5. We need to solve this for x. What do you put into a trig function? An angle measure. You all are hitting your calculators, and I haven't even started the problem yet, so that's good, I think. So when you see cosine of x is equal to negative 2/5, you have to remember that this x represents a what again? An angle measure, a theta, you know, whatever, fish, you know, it's an angle measure. What do you get out of a trig function? Parts of a right triangle, the parts of the two legs of some kind of reference triangle. So angle in, triangle out. How do we get the variable of x, the angle of x, if you will, out of the cosine function? Oh, man, I was afraid you were going to say that.
Well, it's our cosine.
Yeah, but it's not cosine times x. It's cosine of x. The x, the x is inside this math function. We need to get the x out of the math function.
Well, 2 and 5 would be x and r.
True, but, well, yeah, saying x over r now is going to be a little bit confusing because x is over here, but it's an adjacent leg over hypotenuse.
Do the inverse.
Inverse functions. How do you get a variable out of a function? You have to apply an inverse function. If your function is something squared, you apply an square root. If your function's in natural log, you apply an exponential function. If it's like 2x and it's 2 multiplied, you know, if you had multiplication, you divide. But we are going to apply an inverse cosine to both sides of this equation. Now, sometimes I'm going to write the cosine with a little -1 exponent because, you know, it is standard. But I'll be writing arc cosine a lot as well. Now, and the awareness of those restrictions is why I'm starting off with this question. This is actually the most trig we're going to talk about today. Every other example is going to be off the units. You know, we're going to be using, we're going to be able to use unit circle angles. So we'll be speaking more algebra review later today. But inverse cosine of x with the inverse function on the outside or the arc cosine on the outside, those are just going to cancel. And we have now freed the x from the cosine function. And I need to know, since we have the inverse cosine of -2/5, I need the angle measure. What angle measure, because that's what you get from an inverse trig function, what angle measure, you'll need a calculator, inverse cosine of -2/5 is what? I'm requesting x to be in radians, please. And it will be an approximated value because we're using our calculator. All right, I'm just going to do 1.98. So x is approximately 1.98. But that's not the only answer. There's 2. But the calculator can't give you 2. Computers, you know, technology, calculators, computers, they work with functions, not relations. This is one answer. We're looking for solutions that are between 0 and 2 pi. I didn't include that. I should have. We're solving this equation for the interval between 0 and 2 pi. Anybody know how to find the other angle? We talked about this in chapter 4, but you know, we also had winter break and all that stuff, so I'm not surprised that some of you guys are stumped. Let's go back to unit circle stuff. So katoa, right? So ka toa. And cosine of theta is adjacent over hypotenuse. Well, that's fine if you're just finding heights of trees and buildings, but if you're talking about standard position angles and you want to find the trig function of any angle, this is not the best version of the formula. It's the cosine of theta is x over r. Okay, if you want multiple angles, answers that are both acute and obtuse, or basically any measure at all, you have to start, you have to have that theta, that vertex on the origin. You have to have the terminal side on the positive side of the x-axis, and that positive rotation is counterclockwise. Cosine of theta is x over r. R is the distance your point on the terminal side is from the origin, and x is literally a horizontal movement off of the origin. And r x for this specific problem that we're doing is negative. In what quadrants do we have negative x's? 2 and 3. In quadrant 1, you have a positive x and y. In quadrant 2, you have a negative x and y. In quadrant 3, you have a negative x and also a negative y, but I don't really care about that, honestly, because we're talking about cosine. And in quadrant 4, you have a positive x and negative y. So our calculator gave us an answer where? Where is 1.98 radians? Where are 2 radians, basically? We have 0 and pi over 2. 3.14 divided by 2 is 1.57. And then we have pi, which is 3.14. 1.57, 3.14. Where is 2 radians? Quadrant, just say it, 2. So our calculator just gave us our first answer, but not our only answer. And that answer, which is x, is 1.98. Just correctly said that cosine, I know this is inverse cosine, but here, cosine is negative in 2 and 3. We need to use our brains to figure out the other angle that is in quadrant 3. We need our second angle measure. This is a lot of talk over nothing. I mean, you just type it in the calculator. There's no like algebra here. This is all recalling what we learned in the beginning of chapter 4. How do we find theta sub 2? That's fair enough answer. Let's go back a little bit here. What is the sine of pi over 6? 1/2. Man, we're rusty. What's the sine of 5 pi over 6?
1/2.
Also 1/2. What's the sine of 7 pi over 6?
1/2. Negative
A version of 1/2, it's negative 1/2. Why do all 3 of those angles have almost the same answer for sine, which is 1/2? Sine of pi over 6, 1/2. Sine of 5 pi over 6, 1/2. Sine of 7 pi over 6 is negative 1/2. They all have the same reference angle. So if you're going to find the angle that's in quadrant 3 that the calculator cannot give you, you are going to have to find the reference angle. So what how do we find, is really what I need to know. How do we find that reference angle? We've rotated into quadrant 2, which means we're close to pi. Our comparison needs to be against pi. The reference angle is going to be approximately equal to pi minus 1.98, which means it's something. I just did this last period. 1.16, I think? OK. So our reference angle is 1.16 radians, which means our second angle must have a reference angle of 1.16, which means our second answer for 0 to 2 pi, our second answer, our second angle is approximately 3.14 plus 1.16, which is something. 4.3. So this second answer, you actually have to use your brain and remember all of that stuff that we learned in chapter 4. There's a lot of trig that you have to know to just get that second answer. So when you get the test coming up and I'm like, hey, by the way, you're going to be able to use your calculator, those are the ones that you're actually going to have the toughest time with if you don't remember chapter 4. So you got a lot of vocab, a lot of concepts you have to get back in your brain from the first semester. Okay?
This might be a stupid question, but
No stupid questions.
if 1 pi is over here, then how is 1.98 radians right here?
1 pi radians. Let's not forget that when we learned the unit circle, and I was drawing that out, and we had the pi over 4 and pi over 6, and I wrote pi over here. Pi is approximately equal to 3.14 radians. Yeah.
Thank you.
That's how much we work with our unit circle and not calculators. We just forget the super basic stuff. Now, this or these are the two answers, 1.98 and 4.3. I'm probably going to regret that I erased that. Those are our two answers if we want answers between 0 and 2 pi. When you're doing your homework, and this is actually a fair number of the problems, if this restriction is not in the directions, then they want all solutions. That's where the idea of coterminal angles come into play that we talked about in chapter 4, right? The sine of pi over 6 is 1/2, and the sine of 1, why did I do pi over 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The sine of 13 pi over 6 is also going to be 1/2. So if you want all solutions, it's going to be the first angle or the first set of answers. Actually, x of 1 now is kind of not even appropriate. X is equal to approximately equal to 1.96 plus 2 pi n. And the other x's are going to be approximately equal to 4.3 plus 2 pi n, where n is an element of integers. So we have in black our solutions between 0 and 2 pi, and in red we have all solutions. We talked about coterminal angles, reference angles, going back to unit circle setups of x, y, and r, and all of this being said, another thing that you have to remember is your restrictions of your inverse trig functions. So when you have those calculator problems, and you're like, yeah, I get to use a calculator, you actually have to remember the most about trig when using a calculator. Inverse sine or arc sine of, and you might not see it this way, but you're putting in parts of a triangle when you have an inverse trig function. The triangle that goes in, the angle comes out. Arc sine is going to give you answers between negative pi over 2 and positive pi over 2, at least if you're working in radians, and all of calculus is in radians. So you'll be doing lots of radians next year. Arc cosine of x over r is going to give you an angle measure between 0 and pi. We did graph these inverse trig functions last year before the winter break. And arc tangent of y over x is going to give you an answer for theta between negative pi over 2 and positive pi over 2, but of course tangent's undefined when x is 0, so you're not going to be able to include those any angle that puts a terminal side on the y-axis. Holy moly, that was a lot of trig. Okay, let's go back to just using the unit circle and recall now and reuse some of the algebra skills that we know. Our next example of 4 cosine squared of x minus 1 is equal to 0. And let's find our answers between 0 and 2 pi. Our variable is only in one location. right? So when you have something like 2x minus 1 is equal to 7, when you have just one variable, you can just isolate it, right? Just like this is just a two-step equation. Just get the variable alone. We're going to add by 1.
And then divide by 4 cosine squared.
You have to isolate the function that is holding the variable. So let's try this again. 4 cosine of x squared is 4 times the cosine of x, all being raised to a power of 2, which is equal to 1. You need to dig your way down into the variable of x.
So divide by 4 first. Yeah.
So we're going to divide by 4, and we get cosine of x, all of which is a squared, is equal to now to 1/4. And how do we get rid of the power of 2?
Square root.
Square root. See, this way of writing is so much better in terms of being able to follow and identify what sequence of math you need to go through. But it's just a little bit cumbersome to write. Okay, a little bit of side note. Back in, chapter 1, I tried to remind you that x squared square rooted x's absolute values. And when we got done drilling that in and recalling that concept, I then just said, hey, if you introduce your own even root, what do you have to account for?
Plus or minus.
Both the positive and the negative answer, which is coming from that absolute value situation from the something squared square rooted. So we do now have cosine of x is equal to plus or minus 1/2. Some of us might prefer at this point, because it's early on, to write this as two separate equations. We have the cosine of x is equal to 1/2, and the cosine of x is equal to negative 1/2. Now we have two equations where the variable is showing up in just one place, and we need to get the variable of x out of the math function. So then x is going to be the inverse cosine of 1/2. And if you prefer, which honestly I do, you can write this as arc cosine of negative 1, in this case, negative 1/2. Inverse cosine of 1/2. What angle measures give us a cosine value of 1/2 on the unit circle? What angle in quadrant 1 gives you a cosine value of 1/2? Pi over 3, that's right. And what's the other one? Because cosine's also positive in quadrant 4. So pi over 3, 2, 3, 4. I'm into quadrant 4. Right answer, but not right for the directions. I don't want a negative answer. Pi over 3, 2, 3, 4. 5. 5. It's 5. X is equal to pi over 3 and 5 pi over 3. And then arc cosine of negative 1/2. What angles around the unit circle give me a cosine value of negative 1/2? 4 pi over 3. And
You asked me again?
yeah, I am. Oh, wait a minute. You said 4 pi over 3. That's correct. What's the other one? You went all the way into quadrant 3.
And then the other one that gives you negative 1/2 is 2 pi over 3.
Boom. 2 pi over 3. Woo! Okay. Next example. Let's take a look at 2 sine squared x is equal to sine of x plus 3. Getting serious now. The jacket's coming off. The air went off. I'm sweating. Okay. What do we have to do first?
Set the equation on one side.
Thank you. Praise all the math that's good in math. When you have a variable stuck into two functions, you have a sine of x, which is the unknown. I mean, we're going to get, well, it's really the unknown is x, but we have that sine of x inside a power of 2, and we have that sine of x, which is kind of like part of a linear term. When you had, up here, when you had 3x squared is equal to, 2x minus 1, you can't just solve for x, I'm going to just do this. If we have x squared is equal to 2x minus 1, you can't just square root both sides. You'll get x is equal to, and you'll have still an x on the other side of the equation. Most equations are not solved by just getting the variable by itself. Nearly all equations in math are solved by setting them equal to 0. You know, when you get done solving linear equations in Algebra 1 and you go through all that parentheses and two-step equations and equation on, variables on both sides, it seems like you're always just isolating x. No, in real math, you're getting the equation set equal to 0. So like I said, we're going to subtract both sides by sine of x and 3. So we have 2 sine squared x minus sine of x minus 3, and that's equal to 0. Now, this isn't really a polynomial, but this is really kind of like a what? With that power of 2 and then there's a power of 1, this is kind of like what pattern? Not like it is. It's a quadratic. It's not a quadratic polynomial because it's incorrect to call this a polynomial with the sign of x in there. But that is how you're going to approach this problem. You're going to effectively factor this quadratic. So we just did one almost like this yesterday, so I'm going to go through this quicker. 2 times negative 3 is negative 6. And factors of negative 6 that add to negative 1.
It's another 3.
Negative 3 and 2. So we have 2 sine squared of x minus, I'm trying to make something show up here, minus 3 sine of x plus 2 sine of x. If you even need to do this, factoring by grouping. So rewrite the middle term into those using the numbers from the factors of a, c that add to b. Do a factor by grouping. The first two terms have a common factor of sine of x. So the sine of x comes out, and we have 2 sine of x minus 3. Now, when you factor by grouping, you need if it does work, in this parentheses we have a 2 sine of x minus 3. That specific factor needs to show up out of the last two terms. But we already have a 2 sine of x minus 3. So what do we have to show factoring of something. Take out a positive 1. What do these two have in common? What do these two terms have in common? They're the same. But these two terms both have a 2 sine of x minus 3. And when you take that, when you do that factoring, we get 2 sine of x minus 3 times sine of x plus 1. Well, it's almost like this is here. Times sine of x plus 1 is equal to 0. Now, now that we have this quadratic factored, what do we do with each of these factors? Just say it. Set them equal to 0 and then isolate the variables. So we have 2 sine of x minus 3 is 0. We have sine of x plus 1 is 0, giving us sine of x is equal to 3 halves. And the sine of x is equal to negative 1. You might see that 3 halves is not on the unit circle, and thus grab your calculator and try and solve it, but it's going to give you an error. So my question is, really the answer is not error. The answer is does not exist. Why? What's wrong with this?
3 over 2 is not in the domain of arcsine.
That's very mathy sounding and very correct. Someone give me another explanation.
Because 3 is y and the 2 is the r, and y can't be.
What do you put into a trig function? An angle measure. And what do you get out? Parts of a triangle. And that is a opposite leg over a hypotenuse, and a leg cannot be longer than a hypotenuse. Super, super nice job. So don't freak out when your calculator sometimes gives you an error. It's trying to save you. You know how many times a kid comes up and says, my calculator's broken? I'm like, no, it's not the calculator. And what angle gives you a sine value of negative 1? 3 pi over 2. There should not be silence on that question, people. X is 3 pi over 2. Can I just like get you started on the next two problems? Because I don't think we're going to have time to finish. No?
I said why not?
Oh, why not? Okay. Whew. Okay. Gave me permission. Okay. So we have tangent of x squared cosine of x is equal to, how do we solve this equation? Bam! Move that tangent squared over with subtraction. We're going to get this set equal to 0 and have tangent squared x cosine of x minus tangent of x squared is 0. And then, maybe we'll have time to finish all these examples. Now what?
Just kidding, I didn't say that.
Use the F word. Factor. Take out the tangent. Why am I writing in black? Take out the tangent of x squared. Factor it out. You're factoring a monomial. Getting rid of it is a dangerous language. Getting rid of the tangent of x squared sounds like you're dividing it away. Never divide away a variable. You are throwing away answers. You will get some correct answers, but you will not get all of them. Now we have the cosine of x minus 1. Once you factor, you set each factor equal to 0. So we have the tangent squared x is equal to 0. And we have the cosine of x minus 1 is also 0. Square root both sides. We have the tangent of x is equal to 0. X is arc tangent of 0, just for like super perfect every single line of work shown, even though some of us probably will just be able to say the answer. I think for this one, there's no restriction, which I forgot to put on this one. I'm not going to give us a restriction this time, and hopefully it doesn't cause me to run out of time. No 0 to 2 pi, which means we want all solutions. No 0 to 2 pi in the direction means all solutions. So what angle measure gives you a tangent value of 0? At 0 radians, tangent of 0 is 0. Then tangent of pi being y over x, what's the y coordinate over here? 0 over negative 1, that's also 0. What's the tangent of 2 pi? Well, the coordinate is 1, 0, but it's a y value of 0 divided by an x coordinate of 1, so it's also going to be 0. So tangent is 0 starting at 0 plus pi n. So this is going to be x is equal to 0 plus pi n, where n is an element of integers, and that's going to apply to both of these answers. And then over here we have the cosine of x is equal to 1. X is equal to arc cosine of 1. What angle? 0. Okay. Well, I wasn't expecting the same answer. 0. And it would be 0. Okay, 0 is already included, but I'm just going to write this for practice. 1, and it's going to have to go all the way around again, right, to 2 pi, and then 4 pi, and of course you can go in the opposite direction as well. So it's also a 0 plus 2 pi n, but 0 plus 2 pi n is included in our previous answer, so we actually don't need to write that. I'm not going to mark off points if you do. I mean, like, we've already found it. Okay, so I got to go a little bit faster this period so we can finish my last example, I think, or at least get it started. So our last example, it is the last example. So we got 2 cosine of x squared plus 3 sine of x is equal to 0, and I want all I don't want all solutions. I want the solutions between 0 and 2 pi. Anybody see a problem with this? Also on fire today. What's wrong with this?
There's cosine and sine.
So cosine and sine might as well be an x and a y. We had two different variables, two different functions in this equation too, but I didn't get alarmed by it because we could factor them apart. And then that gives us, you know, equations with only one variable. But these will not factor apart. And questions like this are why, you know, what seemed like so long ago I started this discussion with the Pythagorean identities. You need to get this rewritten so it only has one trig function. What's cosine squared x in terms of sine? 1 minus sine squared x. So this can become 2 times 1 minus sine squared x, or sine of x squared, plus 3 sine of x equals 0. Distribute and move things around, and we have negative 2 sine of x squared plus 3 sine of x plus 2. Did I do that wrong?
No, you're right.
I do not like doing, you know, basically this is like a pseudo quadratic. I don't like doing quadratics. I don't like factoring when my leading coefficient is negative. So I'm going to multiply both sides by negative 1, which I'm just going to write once, but encompass the entire equation. This is just personal preference. I don't like negative leading coefficients. So 2 sine of x squared plus, nope, minus 3 sine of x. Is this literally the one we just did? Almost. No, not the same. 2 times negative 2 is negative 4, and factors of negative 4 that add to negative 3? Negative 4 and 1. So 2 sine of x squared minus 4 sine of x plus 1 sine of x minus 2 is 0. Factor out of 2 sine of x, sorry, this is a little bit fast. Sine of x minus 2. Oh, we had that thing. We had this show up again. We already have a match, so we factor out a 1. I tried to make that happen earlier today, and came up anyway. So now we have 2 sine of x plus 1 times sine of x minus 2 is equal to 0, which means we have 2 sine of x minus 1 plus 1 is equal to 0, and sine of x minus 2 is equal to 0, which means we're going to beat the bell. Sine of x is equal to negative 1/2, and sine of x is equal to 2. Is sine ever going to be 2? Nope, you're not going to get a leg longer than a hypotenuse. That cannot be bigger than 1. And we are going to finish. Yay! X is equal to arc sine of negative 1/2, which means x is
7 pi over 6.
7 pi over 6 and
11 pi over 6.
11 pi over 6. Bam! Go do your homework.